Hello everyone. Welcome to my PhD defense. It is a great honor to share some of my work and my reflections. I've spent the better part of the last few years on thinking about efficient and high-quality decision-making for large networks of robots that can coordinate with each other. And for the next 45 to 50 minutes or so, I'll take you on that journey with me. I promise you will leave with an understanding of how hierarchical algorithms can exploit the underlying structure of multi-robot networks to balance their efficiency and quality. Current advancements in robotics research and development will allow networks of autonomous physical agents to operate in dynamic environments and solve a range of tasks. Teams of rovers exploring unknown planetary terrain, fleets of self-driving cars ferrying us to our destinations, and delivery drones promptly getting us our groceries and medicines. A key property of these networks is the potential for some robots to coordinate with each other for mutual benefit. For example, a rover carrying a minicopter up to a suitable release point, self-driving cars platooning on highways, and package-bearing drones riding on vehicles going the same way to save energy. Such coordination can yield cheaper and more energy-efficient networks. This last example on the right will serve as a motivating domain for the rest of the talk, but the underlying formulation and algorithms apply to all of them. Now, let's consider the moving parts of the urban package delivery application. Throughout the thesis, we assume our problem is centralized and fully observable. That is, we have a global and complete picture of all agents. In some area, there is a network of ground vehicles and drones that are ferrying packages from depots to the delivery locations. In addition to flying directly to the destinations and back, which already happens, we want to allow the drones to use the ground vehicles as temporary modes of transit when convenient to save on energy and increase their effective flight range. To do so, we will need to figure out which drone should go where, which vehicle it should use and when it makes sense, without multiple drones getting in each other's way. And we want this operation to scale so it can cover large areas, compute solutions quickly, and try to optimize the real-world costs of time and energy. You might look at all this and say, sure, this is complex and difficult, but we have the well-developed language of optimization to represent and solve the entire problem. So why not just do that? Let's look at some challenges that prevent us from straightforwardly doing that for our entire system. The variables are mixed integer, which are the hardest kind to solve for, and represent decisions for up to hundreds of agents. The total number of variables could be in the millions for real-world problems. The overall objective will be nonlinear in the decision variables over all of the agents, and nonlinear plus mixed integer is generally bad news. There are several constraints to model. Tasks would have time windows to execute them in, drone vehicle interactions would be constrained, and drones have a limited flight range as well. The overall optimization is hard enough on its own. However, the opportunity to coordinate agents while enabling better solutions also makes all the computational aspects of our problem more difficult. A simple example can illustrate how adding just one degree of coordination makes everything harder. Here we have 2 depots, 3 deliveries, and 2 drones, and drones can carry one package at a time. A simple encoding of this problem would have a variable for each triplet of depot, drone, and delivery, which represents the drone delivering the package from and returning to that depot. So 12 variables. Since drones fly directly between locations, the time of flight doesn't change throughout a day, so the ordering of deliveries doesn't matter either. Now, let's add just one transit route with 4 stops. At least 2 things happen to the 12 variables that we can model immediately. First, the route between any depot and delivery becomes time-dependent in terms of the bus route, so the best dispatch depot for a delivery may not be the best return depot, so we multiply by the number of depots again. Second, we just added 4 vertices to the effective route graph because, in principle, any edge from depot or delivery to a bus stop could be considered if the time constraint allows it, The number of all simple paths in a graph is factorial in the number of nodes, so we can add an order 4 factorial. More generally, that means that compared to before, we are at least multiplying by the depots and, more importantly, the factorial of the stops. Beyond just these variables, of course, now the ordering of deliveries is also in play because of the time-dependent nature of the bus network. The ability of a drone to make a further off delivery depends on where and whether it can reach the ground vehicle in time, which now means we have to care more about delays and speedups and missed connections and their downstream effects. And because of all of these challenges, there really has been no prior work on the overall problem of optimizing large-scale multi-robot networks that can coordinate in this manner. And for good reason. Naively trying to optimize the full system would be completely intractable for more than a handful of agents. Certainly, there's been a ton of work on simplified and restricted versions, and I'll mention some of those as we move along. But think of this thesis as trying to fill that gap in the literature. Overall decision-making problems like ours lead to a fundamental trade-off between the computational efficiency of an algorithm and the quality of its solutions. Trivial and simple heuristics are usually the fastest, but can be arbitrarily poor and have no guarantees even under restrictive assumptions, whereas the exact joint solution for the entire system may be far too impractical in space or time. We will be guided by the tenet that we don't need our approaches to be the fastest or the best. We just need them to be fast enough and good enough for the specific needs of the application. And the question then is how we can get them to that region. To understand how this thesis tries to get there, consider our example again. At first blush, it looks like a complex web of intertwined elements that we need to make decisions for: drones, depots, deliveries, ground vehicles, and their interplay with each other. But something that will really help us is that the network we need to solve for is loosely coupled. Intuitively, this means two related things. First, at any given time, only a few agents need to coordinate. So those two drones flying around each other, a drone landing on a bus, and two drones trying to share a bus. Second, if any two agents do coordinate over the span of the problem, the duration of that is small compared to their overall mission. Two drones flying around in an area mostly don't come near each other and only need to interact closely when they do. Here, contrast loose coupling to complete decoupling, where agents don't need to coordinate at all. Loose coupling is a spectrum rather than a binary term. There's no mathematical threshold beyond which a system suddenly stops being loosely coupled. So we will develop a decision-making framework that exploits the extent of loose coupling and benefits the more loosely coupled the system is. The key insight that underpins our framework and this talk is that hierarchical algorithms exploit the loose coupling in multi-robot networks. They do so by solving for smaller subsets of agents and decisions and combining those solutions in a structured manner, as we shall see. If you take one thing away from this talk, let it be this. In line with that central insight, we will take our complex interlocking problem and cut it up into a hierarchy of subproblems, which is fairly standard in multi-robot systems. At the highest level, there's the allocation of tasks to agents, so which drone should make what delivery from what depot. Below that, we need to route the drones to their destinations, deciding whether to use transit, which options, and for how long. Finally, at the lowest level, we'd need some notion of controlling the drones at a suitably high frequency to execute their routes. The loose coupling appears in multiple ways. Since we care about the overall problem, we won't only solve these subproblems in isolation, but also think about their interplay with each other. Additionally, we will revisit loose coupling in each subproblem throughout the talk and observe how our algorithms exploit it. Two running themes that will emerge in the rest of the talk as byproducts of loose coupling are conflict resolution and uncertainty. We can exploit loose coupling to solve for individual or smaller subgroups of agents independently. But since we ultimately have a centralized system with global constraints, we would need to resolve any conflicts between these independent decisions. And second, if we're trying to account for uncertainty in the system, which may be crucial for real-world settings, then we will want to bake that into the design of our framework and think about its effects at all levels. As background, I'll just give a brief overview of the most relevant fundamental concept. The Markov decision process, or MDP, is a mathematical formulation for the sequential decision-making problems we care about here. Let's use this example of a grid world and a drone trying to reach a goal to review the key components of an MDP. A state space captures the information relevant for decision making. Here that could be the position of the agent and the obstacles. The action space contains possible decisions the agent can take at every time step, whether to move or wait. A transition function defines system dynamics and maps state action pairs at time t to a probability distribution over states at t+1. The cost function is the one-step cost of taking an action at a certain state. The negative cost is called the reward. Solving an MDP yields a policy pi that maps states to actions to take. The optimization form can look something like this. We want the policy that minimizes the expected cumulative cost from the initial state over some problem-specific time horizon. Dynamic programming is a broad class of solution techniques that exploits the structure of MDPs through the Bellman equation, one form of which is shown here. The optimal value of a state action pair, the so-called Q value, is the one-step cost of the state action pair plus the expected minimum cost of the next state. There are several nuances and practical variations to this, but the formulation above captures the fundamentals of what matters to us most in the thesis. The technical meat of this talk comprises three parts. I've shown them here in terms of the subproblems that they will involve. The various contributions of the thesis will be grouped under these parts, and I'll summarize them again at the end. The first of the deep dives straddles the allocation and routing layers and will set us up nicely for the other two parts. This paper was nominated for Best Multi-Robot Finalist at last year's ICRA, and an extended version recently appeared in JAIR. Here's a simplified version of an earlier visual. In some city-scale area, we need to control a large number of delivery drones to carry packages from warehouses or depots to the requested locations. Besides flying directly, the drones can use public transit vehicles, say a bus network, as temporary modes of transportation. We need to decide what deliveries to make, in what order, and whether or when to use modes of transit. More concretely, in some geographical area, we have a set of product depots scattered around it. A batch of package delivery requests come in over a business day. We have a bunch of drones that are not necessarily associated with a certain depot. And we're given a network of ground transit routes that are fixed. Our overall objective is to route the drones to deliver the packages while minimizing the make span, that is, minimizing the maximum delivery time of any drone, while respecting the drone flight range constraints. That's our overall problem, regardless of transit. The ability to use transit makes more problems feasible by extending the drone range, but also makes computing solutions more challenging because the problem is larger. In this part, we assume a deterministic setting where the transit network has no delays and the drone has a trivial fixed speed movement model. These assumptions let us focus squarely on the computational challenges of the multi-agent allocation and routing. Our paper builds upon previous research, but they address only subsets of our formulation. Aerial ground delivery pairing approaches typically don't consider more than a few agents. Mobility on demand research is typically unsuitable for agent-based path planning, while the multi-agent pathfinding community has not looked at planning over large time-dependent transit networks. And none of these approaches can be trivially extended to our formulation. The key idea in this part is to loosely couple the problems of allocation and routing that appear here, and then solve them in a two-stage framework. So we have our overall problem of this part, of part 1, that we solve with a two-stage framework. The upper layer is for task allocation. It takes as input the depot and package locations and the drones not associated with any depot, and assigns to each drone a sequence of deliveries and dispatch and return depots for each delivery. The lower layer routes the drones to their next destinations. It takes as input the transit network and the drone start and goal locations from the allocation, and generates detailed paths of flight and transit that respects all the system constraints and the transit timetable, and takes the drones to their destinations. Where the loose coupling arises here is in the proxy travel time estimate that the allocation layer uses, which tries to aggregate and approximate the routing without solving it internally, which would of course be intractable for real-world problems. In this case, the fact that urban transit networks have a regular geographic structure with well-defined timetables allows us to pre-compute good travel time estimates for drones. The allocation uses these to approximate the routing as well as possible. I'll now briefly discuss the allocation at a high level. Again, it takes the depot, package locations and drones as input, and assigns to each drones a sequence of deliveries and dispatch return depots. To compute this allocation, we start with the directed graph of depots Ds and packages Ps. I'm omitting the edges for clarity, but the edge weights are the pre-computed travel time estimate from source to target node locations. And what we want to end up with is a sequence of paths of minimum mix span, one per drone, such that their union visits all package locations once. And how exactly do we get that? Broadly, there are two intermediate steps in this algorithm. We first compute a set of tours on the graph, each of which connects one or more packages to specific dispatch and return depots subject to flow constraints. So, since drones can carry one package at a time, edges can go from depot to package, package to depot, and depot to depot, but not package to package. But remember, we wanted to minimize the maximum delivery time for any drone in our team. So we need something we can distribute across drones such that no one drone takes too long to go between depots from one delivery to another. The next intermediate step then is to merge these tours into a single one by iteratively clustering the nearest sets of depots in each tour. Finally, we take that single tour and split it into chunks of roughly equal cumulative travel time, one per drone, which is what we wanted to end up with. This algorithm has a couple of useful guarantees, but it must make a few assumptions about the problem and graph structure because it solves a multi-agent version of the already hard traveling salesman problem. First, it obtains a near optimal make span in terms of the travel time estimates, where the slack factors are usually small. It also has polynomial runtime in the input size of depots and packages. The bottleneck step can be reduced to the known minimum cost circulation problem, whose relaxed linear program solution is integer optimal. I'll now give a similar high-level summary for the routing. Recall it takes as input the transit network and the drone start goal locations from the allocation layer and computes routes of flight and transit. We obtain bounded suboptimal mix-span routes by enhancing the conflict-based search algorithm. The overall idea of conflict-based search is to plan routes for individual agents independently and then resolve any inter-agent route conflicts that arise by replanning for agents and imposing additional constraints. This resolution proceeds in a structured hierarchical fashion until we get a conflict-free solution in green. There are several algorithmic challenges for using conflict-based search in our case that I won't go into. For each independent per drone route, we take its start, goal, depot package location from the allocation layer. We add them to the transit network graph defined by time-stamped transit stops. We develop an efficient graph search algorithm that computes routes that are bounded suboptimal for each individual drone and also satisfies their flight range constraints. Regarding the conflicts between these independent per drone routes, there are two kinds that might emerge from the transit graph. A boarding conflict occurs when two drones independently attempt to board the same transit option at the same stop. We resolve them by having either drone board at the next stop when it replans. A capacity conflict occurs when the capacity of a transit vehicle is exceeded. We resolve them by having the conflicting drones leave when they replan. To illustrate what all of that lets us do, here's a simple visualization of our entire unified approach in the North San Francisco setting with about 80 drones over a real transit network. We're showing one delivery per drone here, but in practice we can execute them repeatedly over a business day. You can see how several drones use transit when convenient, and at the end you'll see some drones low on energy using transit to get close enough to their return depot and then flying the rest. In terms of evaluation, we first demonstrate that our task allocation implementation is indeed polynomial time in the number of depots and packages. In this surface map, the XY axes are the numbers of depots and packages that we vary. We run the allocation with randomly generated package depot location and plot the average over a bunch of trials. Of course, we sample a few discrete points along the depots and package axes, so it's not really a continuous surface map. The z-coordinate is the log base 2 of the computation time in milliseconds. You can see that it's a roughly linear-ish hyperplane, which means the compute time is between quadratic and cubic in the number of depots and packages, so it matches the theory. In terms of absolute times, I'll just highlight one entry from our larger table. For the setting of 5,000 packages and 10 depots, which could represent a half business day of several hours in an urban area, the allocation time is 18 minutes, which is fast enough for our purposes. To evaluate the routing, we use two real-world public bus networks in their corresponding areas. We get the network information and timetables from the open source GTFS data. In the interest of time, I'll only discuss the San Francisco setting. We varied the number of depot and drones or agents over a city. The depot locations were randomly scattered. For each setting, that is each row of this table, we chose some large number of packages, ran the allocation, and took the set of first package deliveries and returns, one for each drone. We then ran our multi-drone routing on this problem and considered some statistics. We look at median plan time, the maximum range extension and transit vehicle usage, and finally the real-world make span of the set of deliveries. I've highlighted just the extremes in each column here. The solver takes no more than a few seconds on average. Drones use transit quite often, especially when there are fewer depots, and extend their range up to 3.6 or 360%. And the worst make span of about 3,400 seconds is still under an hour. So this is all quite promising for being good enough to deploying these ideas in the real-world context. Okay, so in this part, the core idea was to loosely couple allocation and routing in a two-stage framework and develop efficient yet high-quality algorithms for each stage. By doing so, we obtained fast enough and good enough solutions on real-world scenarios. Earlier I had mentioned two byproducts of loose coupling, conflict resolution and uncertainty. To help us get a global sense of how those themes emerge in this thesis, as we go through the parts we can consider how they are reflected for each decision-making layer. Part 1, which I just spoke about, looked at both allocation and routing and had to resolve conflicts in them both, implicitly in the allocation through the optimization framework, and then explicitly in the routing through conflict-based search. However, we abstracted away the control problem by assuming a trivial fixed speed model for the drones, and we also ignored uncertainty entirely for our convenience. The next part of the talk will look only at allocation, but will try to lift some of the assumptions of the previous one. Before diving in, let me take a quick water break. The paper describing this part was presented at RSS last year and was also invited to the Autonomous Robots Journal. The various challenges we try to account for here, over and above the allocation in the previous work, will all manifest in this little video. Here we assume each delivery has a time window constraint within which the drone can deliver it. We do now consider uncertainty in the drone travel time, which implies uncertainty of executing the task, so some deliveries might be late. And finally, we account for new tasks streaming in online. So in this video, you'll see new delivery tasks as gray rectangles coming in. You'll see the blue en route drone reaching the delivery and returning. And when it does, it's either completed in time, so it's green at that moment, or it's late, so it's red. And if a delivery is unattempted because there was no available drone in the time window, the rectangle is colored red before it disappears. I'll focus on our running example on the left, but in the paper we present a general formulation that models a distinct simulated domain, a team of robot arms arranged along a conveyor belt being dispatched to pick and place objects before they go out of reach. So here we have a set of n agents, k tasks, and a horizon of t time steps, and a time window for each agent to complete each task. Since we only consider allocation, we abstract away the underlying routing and control. We simply model task execution uncertainty as a domain-specific cumulative probability function of an agent completing a task within some time. Given this task execution uncertainty, we seek an allocation policy that maps each agent to a task and a time at which to attempt it. We want this policy to minimize the expected number of incomplete tasks at the end of the horizon, where the constraint enforces that an agent attempt the task in a valid time window. Several research communities approach this sort of problem, but all tend to make one or more simplifying assumptions. The operations research perspective is to think about discrete optimization and network flow, but they typically do not model task uncertainty. The robotics community has worked on multi-robot arm assembly lines, but those methods usually don't generalize to more complex configurations beyond a linear chain. And dynamic vehicle assignment for ride-sharing also works on methods we could apply to multi-robot allocation, but they typically don't model task execution uncertainty in the way we do. Our key idea is to loosely couple the algorithmic challenges of allocating under uncertainty and multi-robot coordination and address them in a hierarchical algorithm. Let me just outline how that hierarchical algorithm proceeds. At the lower level, it computes a single robot allocation independently for each robot and subset of reachable tasks. It uses tree search to reason about the probability of successful task completion within the time windows. For example, for drone N1 and deliveries K1 and K2, the tree encodes whether to attempt or to leave K1 and then attempt or leave K2 with some branch-dependent probability. Since the lower level tree searches are run independently per robot, also for N2 and N3 and so on, conflicts may arise due to multiple robots attempting the same task in overlapping windows. At the higher level, we then coordinate the allocation policies of each robot using conflict resolution logic. This is our friend conflict-based search that we saw for the routing in part 1. But here we are resolving conflicts not between routes, as we were in part 1, but between task allocations. In contrast to the previous part, where each level was itself solving a large problem and we had to make it a two-stage algorithm, one after the other, here we can afford to have the higher and lower levels work repeatedly to obtain a conflict-free multi-robot allocation. We show in the paper how our algorithm, stochastic conflict-based allocation or SCOBA, is optimal in expectation for the given uncertainty model and complete under some assumptions. More importantly, its elegant representation allows us to interleave planning and execution online as new tasks come streaming in. You can cut off the horizon of the tree search and the conflict resolution. Again, I'll only discuss results for our running domain. For solution quality, we considered the number of task failures at the end of the problem horizon, as well as the computation time. For the fail task penalty metric, we baseline SCOBA against a range of allocation approaches, such as the earliest due date heuristic, a variant of the Hungarian matching algorithm, and by framing it as an MDP and applying Monte Carlo tree search, or MCTS. Here, our metric is the fraction of late package deliveries after running the simulation up to some horizon, so lower is better. Notice that SCOBA in orange mostly outperforms all applicable baselines across different problem parameters. We vary the probability of a new package request coming in at each minute to vary the difficulty. We also define different settings of depots and drones to vary the amount of coverage over the problem, another axis of difficulty. In contrast to part 1, here we equally distribute drones across depots a priori. You can see that in absolute terms, the 5 depots 15 drones setting, the middle chart, is the hardest because the number of drones per depots is the fewest. We also looked at the computation time of SCOBA and how it scales with depots, drones, and tasks. We show the mean and standard error over 50 trials for each setting. The absolute wall clock times are good enough considering the time scale of operation is in business minutes and hours. The standard error of some settings is a bit higher because the variance is higher as there are more conflicts to resolve. So, in this part, we loosely coupled the problems of allocation, under uncertainty, and multi-robot coordination and addressed them hierarchically. Returning to the table of themes, part 2 only considered allocation, but within it, it did account for uncertainty and did have to worry about resolving conflicts between individual agents. The third part of the talk will look at the other end of the decision-making hierarchy, computing per time step control actions to execute those routes. We developed it as a general-purpose planning algorithm for multi-agent MDPs. It was awarded Best Paper at AMAS just last week. Here we focus on the subset of our overall problem where, having obtained tasks and then routes from the upper layers, multiple package delivery drones need to navigate to specific landing locations nearby without getting too close to each other. They must also coordinate their landing such that only one drone lands on a bus at a time. We model this as a multi-agent extension of the Markov decision process, or MMDP, where our objective is to compute actions for all agents to maximize the cumulative reward at the end of the horizon. Let's reuse our simple grid world example from earlier to understand the challenges of MMDPs. In theory, we could just reduce it to a single agent MDP with a joint state action space for all agents. However, these spaces grow exponentially in the size of the team. For 5 drones, the state space of 9 by 9 grid cells becomes 81 to the 5, and the action space becomes 5 to the 5. On real-world problems with large spaces, solving MMDPs jointly becomes intractable very quickly. We might then think of solving an MDP for each single agent independently and combining their decisions. But in domains where we need to worry about the interactions between agents and their coordination, this strategy can be arbitrarily suboptimal, for example, violating safety thresholds or causing deadlocks. So again, we have the perennial trade-off, the extremes of intractable optimality and highly suboptimal efficiency. Our key idea here no surprise by now, is loose coupling. In the MMDP context, that means to loosely couple the joint agent actions and exploit any sparsity in their coordination. And how exactly do we do that? Most real-world MMDPs have some locality in their interactions. That is, the effective outcome of an agent's action only depends on a subset of other agent actions. For example, only drones close enough to each other need to coordinate and are connected by dotted lines. We can abstractly encode this locality with the coordination graph, or CG. The nodes represent agents, and the edges connect agents that need to coordinate their control actions. Of course, the CG is still a factored approximation of the true system, but here we will assume it correctly captures the sparsity of coordination. Given a CG, we can solve the MMDP more efficiently through factored value functions and coordination algorithms. The idea is to factor the joint state action or Q function, state action value or Q function, in terms of individual agent utilities and pairwise payoff functions for the nodes and edges of the CG respectively. Given the factored representation and the individual and pairwise over the edges Q functions, we can compute the best joint action for the current state, which is hidden in the equations, with the MaxPlus algorithm. In MaxPlus, each agent iteratively sends messages to its neighbors in the CG. Each message is a real-valued function of the action space of the receiving agent. Each message depends on the sending agent's utility, the pairwise payoff, and the messages from other neighbors in the previous round. Agents exchange messages until convergence. And finally, each agent computes its optimal action individually, using its own utility and final incoming messages. So all of this allows us to exploit the sparsity of coordination in the action space at the current state. But this only computes the best control action for the current state and its current coordination graph. How do we plan sequentially under uncertainty with a potentially changing coordination graph structure? To do that, we unite factored value functions and MaxPlus with Monte Carlo tree search, which is an online approach that interleaves planning and execution, only considering states that are reachable from the current state. So the tree search explores from the current joint state S bar and tracks statistics about the simulated value of trying various joint actions. We use MaxPlus at the joint state to compute an exploratory multi-agent action A bar 1 and reach the next simulated state S bar prime, from which we can compute and try various actions again. This procedure is repeated for various Monte Carlo trials, yielding different next simulated states S double prime with a rollout to estimate the value of leaf nodes. The results of these simulations update statistics at the root node. After running the tree search for some number of trials, we use the final Q statistics to compute the best next action A star to take at the current state in a last MaxPlus step. After taking this action, we reach the next state and rinse and repeat. I'm skipping over the intricate algorithmic details, but I will point out how our approach allows us to use dynamic or state-dependent coordination graphs. From our earlier example, let's say we reach two intermediate states with different CG topologies. So now there are multiple different CG topologies in the same tree itself. But MaxPlus just reasons over the nodes and edges of the CG, not its topology. There are 4 CG nodes because 4 agents, and at most 4 choose 2 edges. So we can simply maintain and update statistics for the relevant CG nodes and edges even as the topology might change. And that really lets us exploit the loose coupling to a whole new level compared to prior work, which is also why I omitted discussing related work in the interest of time. We developed our algorithm as a general purpose MMDP planner and evaluated on 2 distinct domains. Of course, I'll stick to our running example of multiple package delivery drones navigating to landing locations. The dynamic coordination graph for the domain is defined based on the shared landing goal locations of the agents and the distance between them, which can change. For this paper, just one plot suffices to highlight both scale efficiency and quality with respect to the baselines. But what are those baselines? We have a policy that chooses actions at random. We solve independently for each agent with Q-learning and combine their decisions. We run MCTS on the full joint problem with joint state action spaces. We have a previously introduced factored value MCTS that uses the exact variable elimination algorithm, and then our approach with MaxPlus. For various initial conditions, we ran each approach for some horizon, add up the cumulative reward, so higher is better, where agents are penalized for moving or getting too close to each other and rewarded for reaching their goal. Several things to notice here. First, the independent approach never learns anything useful, so we only show it once on the leftmost axis, the blue circle. For 8 agents, the leftmost line, our approach in the orange cross is slightly better than the variant with variable elimination, the blue cross, and much better than the others. Joint MCTS, the pink star, runs out of memory even for 8 agents and is right there at the bottom. For more agents, 16 and 32, even Varel, the blue cross, runs out of memory because it is more space hungry, even as our approach maintains good performance. So we can see how it strictly dominates other MCTS variants on both efficiency and quality. So the key idea of this part was to address the control problem in MMDPs by loosely coupling the joint actions and exploiting the sparsity in the dynamic coordination graph with MaxPlus and MCTS. Coming back to our themes table, this part only considered the control level of the decision hierarchy. Within it, we can, of course, account for uncertainty through the transition function of the MMDP. We don't explicitly talk about conflict resolution, but if two control actions of neighboring agents conflict with each other, we can reject it. Alright, the end is in sight. For the last few minutes, let's take a step back and look at the thesis as a whole. I'll summarize the overall contributions and provide a few high-level insights. We presented a decision-making hierarchy for coordinated multi-robot networks. Strictly speaking, this hierarchy cannot lay claim to novelty, but where we do contribute something is the manner in which the algorithms of our hierarchy explicitly consider the challenges and benefits of coordination at every level, as they try to balance efficiency with solution quality. The various theoretical and algorithmic contributions were distributed in the 3 parts that I discussed. A 4th part that I omitted to talk about, both in the interest of time and because it only considers single agent settings, but it looks at how to interleave the routing and control subproblems. To put the omitted part into the context of our running themes table, it considers routing and control and uncertainty at both levels, but since it is a single agent algorithm, there's no explicit conflict resolution. Looking at the entire table now, we can see a global picture emerge, where every theme for each subproblem is addressed by some algorithm somewhere. This table can give us a roadmap for the natural question of how we might integrate all of these together into a well-engineered comprehensive system that can account for uncertainty and resolve conflicts at every level of the hierarchy. The actual system integration, of course, would be a considerable enterprise beyond the scope of one PhD student. We now return to our central insight. Hierarchical algorithms exploit loose coupling in multi-robot networks. And we recognize how it aligns with our tenet that we just need to be good enough and fast enough. The loose coupling in the whole system and in every subproblem yields underlying structure our algorithms use to solve the problem fast enough. But if we only solve for the subproblems, we might have poor quality solutions. The hierarchical nature of coordinating and resolving conflicts between agents, or using estimates to approximate lower layers, yield solutions that are then good enough for our purposes. Together, they underpin this thesis and how it gets to that region. Beyond the core insight of loose coupling, we can now reflect on some other qualitative insights from a global view. The first just reiterates the premise that agents coordinating potentially dynamically could lead to better solutions at the cost of more complexity. We saw in part 1 how drones extended their range by using transit, and in part 3 how our approach outperformed the baselines that don't consider dynamic coordination. Second, though we discuss separate algorithms for various layers, our consistent design choices of data structures and representations, tree search for example, could allow a system to effectively combine them, and the 4-part table from earlier gives us a roadmap for the same. Last but not least, the thesis has mostly been extolling the virtues of hierarchical algorithms and loose coupling to solve multi-agent problems. But of course they are no magic bullet, because the underlying multi-agent decision problems are all NP-hard. They only work well to the extent that the system actually is loosely coupled and there actually is some sparse structure to exploit, which is mostly true for our settings. But if that is not the case, if the system is tightly coupled and there are many and complex conflicts to resolve, as we sometimes encounter, then our methods can be quite expensive. In terms of interesting future work, I see 3 broad areas. First is extending the algorithmic and modeling capabilities. We could look at optimizing depot placement or jointly routing the ground and aerial vehicles. Second, all of our algorithms were inherently model-based, so one immediate extension is for data-driven models that best balance efficiency and quality. Beyond that, we could also look at using experience more broadly to augment the decision-making algorithms themselves. Instead of relying on a predefined set of rules for coordination graphs, we could think about learning an implicit dynamic CG structure through interactions with the environment. Also, we could extend the influential idea of augmenting tree search with learned heuristics and rollout strategies to factored multi-agent settings. Third, to aid our understanding of the real-world aspects of deployment, even for high-level decision-making, we'd benefit from case studies that estimate the operational cost of our framework, evaluate its real-world impact, and consider potential negative externalities. The open source Julia repositories in this GitHub snapshot are the backbone for all of the code in this thesis and have been used by other researchers as well. I hope that my work has helped paint a picture of how, in a future where multi-robot networks will operate in a range of environments and applications, the kind of coordination I've talked about can help them be better, cheaper, and more efficient. And that's a pretty strong incentive. That brings me to the end of my thesis talk. I'd like to thank the various funding sources that supported me and our work, and thank you very much for your attention.